Welcome to G Fun Facts Online. Today we are turning our gaze roughly 2 billion miles outward, toward the dark, cold edges of our solar system. For a long time, the ice giants, Uranus and Neptune, were seen as the quiet, perhaps even boring siblings of the gas giants Jupiter and Saturn. But recent discoveries have shattered that illusion, revealing systems that are chaotic, violent, and exquisitely complex. The headline that has reignited this interest is the identification of S2023U1, the 28th moon of Uranus. This is not just an incremental addition to a planetary catalog. It is a key that unlocks a broader discussion on how these distant worlds formed and how they are still evolving today. We are going to skip the long introductions and dive straight into the physics, the discovery, and the chaotic clockwork of the Uranian system. Let us begin with the discovery itself. In early 2024, the Minor Planet Center announced the existence of this new satellite. It was identified by astronomer Scott Shepard using the 6.5-meter Magellan-Bade telescope at the Las Campanas Observatory in Chile. Now, finding a moon at this distance is not like pointing a telescope at the sky and taking a picture. Uranus is so far away that the reflected light from the planet can easily wash out the faint signature of a small rock. S2023U1 is only about 8 kilometers or 5 miles in diameter. Finding it is akin to spotting a candle on the rim of a lighthouse from miles away. To achieve this, astronomers used a technique known as shift and add processing. This is a brilliant method where they take dozens of long exposure images over a period of time. Because the moon is moving relative to the background stars, simply stacking the images would smear the moon into invisibility. Instead, they digitally shift each image to match the predicted motion of Uranus. When these shifted images are stacked, the light from the moon piles up on top of itself, becoming brighter, while the background stars streak and blur out. This technique revealed S2023U1 as a faint point of light with a magnitude of 26.7. To put that in perspective, that is millions of times fainter than what the human eye can see. But what is this object? It is classified as an irregular satellite. In planetary science, irregular does not just mean weird. It has a specific definition. Regular moons orbit in the planet's equatorial plane, usually close in. Irregular moons, like this new discovery, follow distant, highly eccentric, and often retrograde orbits. S2023U1 orbits at an average distance of approximately 8 million kilometers from Uranus. A single trip around the planet takes it roughly 680 days, which is almost 2 Earth years. Most tellingly, its orbit is tilted at approximately 144 degrees relative to the ecliptic. This means it travels backwards compared to the rotation of the planet. Dynamical analysis places this new moon within the Caliban group. These are objects that share similar orbital elements, which tells us a story about their past. It suggests that they are likely fragments of a single, larger parent body that was shattered by a collision billions of years ago. The discovery of this 28th moon supports the theory that the outer Uranian system is essentially a debris field of captured objects, frozen in the midst of a multi-billion-year collisional cascade. This brings us to the architecture of capture. The existence of S2023U1 challenges the simple model where moons form from a dusty disk surrounding an infant planet. These outer moons are immigrants, not natives. To understand why Uranus has a swarm of distant retrograde moons, we must look to the nice model of solar system evolution. This theory suggests that about 4 billion years ago, the giant planets migrated significantly. Uranus and Neptune were likely pushed outward into a primordial disk of icy debris known as the Kuiper Belt. As the ice giants plowed through this debris, their gravity acted like a net. Through 3 body interactions involving the Sun, the planet, and the planetesimal, Uranus was able to capture passing objects. It is dynamically easier to capture an object into a retrograde orbit, one moving opposite to the planet, than a prograde one. This explains why the majority of Uranus' outer moons, including our new discovery, orbit in this backward direction. Once captured, these moons are not just left to drift peacefully, they are subjected to the Kozai-Lidov mechanism. This is a secular resonance that acts like a trade-off between eccentricity and inclination. For a moon in a highly inclined orbit, the gravitational tug of the Sun can cause its orbit to become rounder, but more tilted, or more elliptical but flatter, in a periodic cycle. This mechanism dictates the stability zones where moons can exist. If an orbit becomes too eccentric due to this cycle, the moon might crash into the planet or be thrown out of the system entirely. S2023U1 resides in a stable island of phase space, where it is safe from these destabilizing effects, likely for the age of the solar system. While the outer system is a relic of ancient capture, the inner system of Uranus is a different beast entirely. This is the realm of the rings and the Portia group of moons. It is a dynamic, chaotic environment that is evolving on human timescales. The region between the main rings of Uranus and the large moon Miranda is the most crowded real estate in the solar system. It is packed with small satellites like Cordelia, Ophelia, Bianca, Cressida, Desdemona, Juliet, Portia, Rosalind, Cupid, Belinda, and Perdita. This cluster, often called the Portia group, is so tightly packed that their gravitational interactions are chaotic. Dynamical simulations predict that the orbits of Cressida and Desdemona will intersect within the next 1 to 10 million years. In cosmic time, that is the blink of an eye. When these moons inevitably collide, they will pulverize each other, creating a massive debris cloud. This cloud will spread out to form a new ring, which will eventually reaccrete into new, smaller moons. This cyclic process of collision and rebirth suggests that the inner moons we see today are likely Generation 3 or Generation 4 descendants of the original satellites. We are watching a slow-motion car crash that has been running for billions of years. A prime example of this instability is the mystery of Cupid and Belinda. The tiny moon Cupid was discovered by the Hubble Space Telescope in 2003. It orbits only 800 kilometers away from the moon Belinda. Recent studies suggest that the Belinda group is kept temporarily stable by a delicate web of mean motion resonances, where the orbital periods are integer ratios. However, dynamical models have shown that the Belinda-Cupid pair is so unstable that they could collide at any time. Some astronomers even speculate that strange dusty features seen in the rings could be the aftermath of unobserved collisions between smaller, unseen moonlets that have already happened. Speaking of rings, the dynamics of the Uranian rings are fundamentally different from Saturn's broad, bright sheets of ice. Uranus has narrow, dark, and sharp-edged rings. These characteristics pose a major problem for classical orbital mechanics, known as the confinement problem. Without intervention, a narrow ring of particles should spread out due to collisions and drag forces. A ring as narrow as Uranus' Epsilon ring, which is only 20 to 100 kilometers wide, should dissipate in just a few million years. The fact that they are still there implies an active confinement mechanism. The standard solution is shepherd moons. For the Epsilon ring, we have identified Cordelia orbiting just inside and Ophelia just outside. Their combined gravitational torques keep the ring focused. However, for many of the other narrow rings like Alpha, Beta, and Gamma, no shepherd moons have been found. This suggests one of two things. Either the shepherds are too small to be seen, likely less than 10 kilometers in diameter, or there is a different dynamical mechanism at play. This brings us to Lindblad resonances. The dynamics of the Uranian rings are heavily influenced by these resonances, which occur when the natural orbital frequency of a ring particle matches a forcing frequency from a moon. Instead of simply scattering particles, these resonances can launch density waves. Think of these as spiral patterns that wind through the rings like grooves on a vinyl record. Analysis of the ring edges suggests they are often truncated exactly at these resonance locations. This indicates that distant moons like Portia and Rosalind are remotely sculpting the rings, acting as virtual shepherds. One of the most fascinating dynamical systems is the relationship between the small moon MAB and the diffuse mu ring. MAB is too small to hold onto an atmosphere or a geologically active surface. However, it is constantly bombarded by micrometeoroids. This bombardment ejects dust from MAB's surface. Because MAB has such low gravity, the dust escapes and forms a torus along the moon's orbit. This creates the mu ring. This ring is blue, which is rare in the solar system, indicating the dust is made of tiny, submicron particles of pure water ice. It is a regenerative system where MAB creates the ring, and the ring likely slowly reaccretes onto MAB. To fully appreciate the unique nature of Uranus, we must compare it to its twin, Neptune. Despite their similar mass and composition, their dynamical histories diverged radically. The Uranian system is tilted 98 degrees, likely the result of a massive grazing impact with an Earth-sized protoplanet shortly after formation. This impact spun out a debris disk from which the regular moons formed in situ. This explains why the moons orbit the equator, even though the equator is vertical relative to the solar system. Neptune, on the other hand, had its system disrupted by the capture of Triton. Triton is a Kuiper Belt object, likely larger than Pluto, that was captured into a retrograde orbit. This violent event likely destroyed Neptune's original moon system, scattering debris that eventually settled into the current, sparse ring system. This difference is visible in their rings. Uranus has dense, complete, narrow rings. Neptune has ring arcs, which are clumps of dust that do not go all the way around the planet. The Adam's ring of Neptune, for instance, has 5 distinct arcs named Courage, Liberté, Aegalite 1, Aegalite 2, and Fraternite. These arcs are confined by a co-rotation resonance with the moon Galatea. The gravity of Galatea prevents the dust from spreading out into a full ring, trapping it in specific stable points along the orbit. This is a dynamical regime unique to the Neptunian system. As we look to the future, the discovery of S2023-U1 is a reminder of how much remains hidden. The 2023 Planetary Science Decadal Survey listed a Uranus orbiter and probe as the highest priority flagship mission for NASA. This mission, hoping to arrive in the 2040s, aims to map the gravity field of the inner system to detect the missing shepherds and understand the mass distribution of the rings. The mission trajectory would likely include flybys of irregular moons to determine their density and composition, testing the hypothesis that they are chemically identical to Kuiper Belt objects. S-2023, the first of may be small, but it is a survivor. It has survived the chaos of the early solar system, the migration of the giants, and eons of isolation. Its discovery helps astronomers calibrate their models of how many small bodies lurk in the outer halos of the giants. Current estimates suggest Uranus could have hundreds of such moonlets waiting for the next generation of extremely large telescopes to reveal them. In conclusion, the Uranian system is a paradoxical realm. Its outer reaches are a frozen museum of the solar system's chaotic youth, preserving the history of planetary migration. Its inner reaches are a frantic, evolving machine where moons are destroyed and rings are born in a cycle of violence. Understanding the dynamics of this system, from the eccentric wanderings of its 28th moon to the resonant confinement of its razor-thin rings, provides a crucial window into the physical laws that shape not just our solar system, but the countless exoplanetary systems now being discovered across the galaxy. As we prepare to return to the ice giants, every new moon discovered is a breadcrumb, leading us closer to understanding our cosmic origins. This has been Fun Facts Online. Thank you for listening.